Thank you for introduction. So let me explain the background of my talk. The backgrounds are CGF and MLTT. To formalize Bishop's constructive analysis, actually introduced a system of construct set theory called CGA. Here, several set theoretic principles and set existence actions were codified on the basis of first-order integer logic with equality. Thank you. On the other hand, Martin-Löf took a different approach. He formulated a framework of construct type theory called MLTT. And actually also shows that these two approaches are compatible. He defined a cumulative hierarchy of sets as a W type in MLTT and interpreted all axioms of CGF in MLTT. V is a type with this equivalence motion, which is similar to bisimulation. Informally, each set can be considered in this way, Here, index A is the type of indices for the elements of A, and the predecessor AX is X of type index A is the element of A of index X. So each set has its indices, and it consists of the predecessor sets of these indices. Then the membership relation is defined in this way. Namely, A is equal to some predecessor set of B. As in classical Zermelo-Fraenkel set theory, the transitive closure of a set can be defined in CGA. So the transitive closure of a set of A satisfies this equation. But in this talk, we can ignore this detail. The point is that transitive closure of A contains as its elements all sets before A in this cumulative hierarchy. Then through Axel's interpretation of CGF, one has a corresponding operator, TC in MLTT. And by using TBS index inductive definition, one can then define the so-called accessibility predicate ACK on the cumulative hierarchy. Here, I use the logical framework in Agda. So we use this abbreviation, and the meaning of ACK is as follows. ACK says that a set A is constructed from below. So the constructor progressive says that for any set X below A in this hierarchy is accessible, then A is also accessible. A is constructed from below. Then the accessibility predicate has this induction principle. But again, we can ignore this detail. But please note that the accessibility predicate has this relatively simple computation rule. Here are the properties of accessibility. The induction principle for ACK is stronger than V induction, namely the W induction principle on V, because the former admits the induction hypothesis not only for each V in A, namely the immediate element of A, but also for each W in TCA, namely any set W below A in this hierarchy. For example, we can define a universe type U indexed with a set A containing as its subuniverses not only UV for any V in A, but also UW for any W in TCA. And the ACK induction principle has the simple computation rule. In fact, the transitive closure operator is accompanied by similar induction principle in the TC, which is stronger than V induction 2. But this elevator induction principle for TC operator lacks a simple computation rule. So let's see this. One might try to show that the eliminator for TC induction principle has a following computation law. This is eliminator, and P is a predicate for induction. H is an inductive cause, and A is an argument. Then this term computes to the right-hand side. H, A, and here we have the induction hypothesis. But this is a non-terminating rule, so we cannot derive this rule in, for example, intentional Martin-Löf type theory, because that theory is terminating. So if we compute this red part, then we have this term. And we can compute this red part again, then by X rule, we have this term, and so on. So here we have a non-terminating term. So we cannot derive this rule in intentional Martin-Löf type theory. But this situation will change in the presence of function extensionality, and our aim is to verify this. We first showed in MLTT with function extensionality, the above computation rule of TC induction principle holds propositionally. And with this propositional computation rule, CompTC, the TC induction principle provides a useful inductive definition. Then we verify the accessibility arc on the cumulative hierarchy is definable by means of this proportional computation rule without index inductive definition. By using CompTC, we have this definitional equation for arc. Here, the constructor progressive is defined by transporting from the right-hand side to left-hand side. So, from this way. Then the arc induction principle is defined by transporting in the opposite direction. Finally, by using functional extensionality again, we show that the type arc A has a unique inhabitant for any set A. And we have formalized these results in Agda. So if you are interested in this formalization, please read my abstract. Here, this is a standard formulation of functional extensionality. And first of all, without functional extensionality, we derive the TC induction principle. So here is a predicate P. And if we can prove PA under the assumption that or any set X below A satisfies P, then we can derive or any set A, PA holds. And with functional extensionality, we have this proportional computation rule, or TC induction principle. Then, next our aim is to define arc. Putting P, a predicate for induction, in this way, then we define arc, an inductive clause for arc is defined like this. And we define predicate arc in this way. Then, by using the proportional computation rule for TC induction, namely CompTC, we have this definitional equation for arc. Then, as we have seen, by transporting from right-hand side to left-hand side, we have this constructor progressive. And then, if we go in the opposite direction, we have this operator inversion, or any set X A, or any set A. If A is accessible, then yeah, we have this fact. And our idea to derive the induction principle is as follows. But unfortunately, we cannot enter into the detail. Anyway, we need to prove PAC, A and C satisfy some predicate P. And first, by transporting along this definitional equation for AC, we have PA prog A in AC. Namely, we first go along this equation from the right-hand side to left-hand side, and then, sorry. We first go left-hand side to right-hand side by using inversion. And then we going back to this equation by using progressive operator. Then by a general fact on transport, we can cancel this trip. So from PA prog A in AC, we can prove PAC. This is a basic idea. And then finally, we can prove the uniqueness of AC A. We first verify that for any set A, AC A holds. And then we show, for any proof of AC A, TS, T and S are equal by TC induction on A. For any TS of type AC A, first we have these facts by inversion operator. Then, as induction hypothesis, we can assume that for any set X below A, AC X has a unique proof. So we can identify these terms. Then, by using function extensionality, we have this equation for functions. And then the congruence with progress A gives this equality. Finally, we can cancel the both sides as above, and we obtain this equation. So AC A has a unique proof. This is a slide for future work. Interestingly, Axel's interpretation of CZF in MLTT was refined in homotopy type theory. The cumulative hierarchy of sets is defined not as a W type, but as a higher inductive type. The equivalence relation on V is replaced with the identity type, and V has a path constructor. And other interpretation of CZF in HOT were investigated in, for example, these papers. In the literature of HOT, the accessible part of binary relation is defined by indexed inductive definition. And as a future work, we will examine in some HOT interpretation of CZF whether the TC induction principle and its proportional computation rule are derivable, and whether the accessibility on V is definable without indexed inductive definition. So that's all. Thank you.